The next group is Department of Industrial Informatics, which is a group headed by myself. So I will briefly say about our publications that have been either accepted or that have been published in 2024. So we can see here two publications in International Journal of Operations Research, which is a very highly cited journal, and then the best results has achieved Mohammed, who is co-author of several of those papers, but we see also publications in multiple transactional and intelligent transportation systems, in computers and operation research and so on, typically solving scheduling and combinatorial optimization problems. A part of that, from the team of Lukáš Krpa, we have three nice papers in core A-star conferences, ICAPS and ICHCAR. So that's about publications. We typically have quite broad collaboration with industry, which was also continuing in 2024. Unfortunately, the budgets are, especially of automotive companies, are shrinking. So we probably in the future will have less financial income from that. But I hope that we will still keep like expert collaboration with them. It was about autonomous driving, about simulation of some external components in automotive, and also about energy efficient energy production, robotic production, sorry. As far for today, we have 4 talks. As probably you might know, I'm principal investigator of the RoboProx project, and as such I have a lot of duties related to management and administration of that project. So I'm happy to announce that Professor Šůcha, who is the first speaker, will be head of the department starting from the 1st of February. But don't be sad, I am still here, so you can meet me and invite me for lunch if you want. Okay, so Przemek, please come here, and the floor is yours.
Good morning. I will present today joint work with Pavlína Koutecká, who is our former master student, Jan Hula, and Bruce Manhood from Ghent University. And I will talk about improvement of this method using machine learning. First of all, I will just quickly introduce what the branch and price is, because that's in combinatorial optimization very famous method, and it's a state-of-the-art method for many combinatorial problems so far. The method is based on so-called Danzig-Wolf decomposition, which, unlike traditional approaches where you look at the problem from the global perspective, you make all the decisions at once. Decomposition focuses on specific sub-problems that we can identify in the combinatorial problem. A typical example is the vehicle routing problem, which is the problem you might know from classes of combinatorial optimization. It's a problem where you have a fleet of vehicles, set of places defined by a graph, and you need to cover those places by routes. So it's good distribution. Those are this type of application. This is a classical example where you can apply branch and price and Danzig-Wolf decomposition. So the idea is that instead of making particle decisions, we construct individual routes, like it is illustrated in the figure on the top right. So here is a trivial example with 3 routes, 0, 1, 0, 2, and 0, 3, and that corresponds to the appropriate master problem, having 3 decision variables saying whether we will use that route or not. Of course, this is not enough. We might have much more routes, and therefore the routes are generated at runtime, so we add them one after another, because we cannot assume all of them at once, because there would be exponential number of them, and therefore we have so-called sub-problem that continuously generate new routes. The branching price is like relatively complex approach, but I will just briefly introduce the main components because it's important to explain our idea. The core part of the branching price is column generation, which solves the linear relaxation of the problem, and the integrality of solution is handled by so-called branching, which is in fact just the branch and bound approach, and altogether this is called branching price. Column generation, as I already mentioned, has two parts. It's the master problem that combines the roots in case of the vehicle routing problem, and one or multiple subproblems that solves like the decomposed problems, some particle subproblems of the whole problem. Another purpose of the subproblem is to detect whether we can stop the generation of new columns, or sometimes called new patterns, the roots. It is based on the reduced cost. If none of the subproblem is able to find a solution with the negative reduced cost, then we can stop the column generation. And actually, the good property of this algorithm is that like there are many places where we can apply some improvement, and also the improvement can be based on machine learning. The idea of like applying machine learning to the branching price is not new. Nevertheless, the first paper in this direction was ours. It's Václavík. Another co-author is Tonda Novák, me, and Zdeněk Hanzálek. It was the first paper that tried to successfully applied machine learning to speed up the branching price algorithm. Apart from that, you see that there are like many other papers. Mostly they concentrate on speeding up the subproblem, but often issue, it is highlighted in the table, they often don't guarantee the optimality of the overall approach, and none of them concentrate on how to manage execution of individual subproblems. And this is the weakness, and that's what we addressed in our paper. Hopefully, our idea is like very simple and can be illustrated just using those two figures. So we run the standard branch and price algorithm on some smaller instances, and we monitor interaction between the master problem and subproblems. So detect dual solutions, we detect reduced costs obtained by the subproblems, and we record that. Then we train a ranker, meaning a machine learning based model, which is able to rank the subproblems regarding the reduced cost. So we get like estimate which subproblem should be has a higher chance to achieve solution that can add a new column, new pattern into the master problem, and we solve them according in this order. So if we get one successful solution, then the good news is that we can ignore other subproblems and thus save some time. And that's our idea. We apply this idea to operating room planning and scheduling problem. It's a problem given by a set of patients on a waiting list. So we talk about elective patients, set of operating rooms, and a set of blocks defining availability of surgeons. And the objective is to assign patients to blocks such that we minimize some objective, which minimizes waiting time of patients, number of non-planned surgeries, operation room overtime, and underutilization. Here, the decomposition is based on the block, so it means that we assign and schedule operations in individual block via subproblems, and we apply our idea and try different models for the ranking. So we assume like 3 possible model types: burst-wise, list-wise, and point-wise. And the best one was lambda mart with precision 0.92. We implemented this idea into the branch and price approach, and we managed to reduce up to 41% of subproblems, so we were able to skip them compared to the standard approach, and it resulted into saving about 10% of the CPU time. Next slide, please. So to conclude, we developed like completely new method to speed up the branch and price. It exploits the advantage of this decomposition algorithm, and we have like very efficient way to generate the training data, because from single instance we are able to derive like more training samples we can use to train the ranker. And the algorithm was applied to a practical planning and scheduling problem. And currently we are preparing a project with Motol University Hospital about surgery planning and scheduling. Result was published in European Journal of Operations Research. This is a Q1 journal, and we continue with those ideas together with team of Mikuláš Janota, and we investigate like other opportunities in this domain further. Thank you very much for your attention.
Hello, my name is Mohammed. Today is my pleasure to talk about one of our current research regarding optimal trading strategy in electricity market for the charging station company, which serve both electrical and hydrogen vehicles. Next. Let's me start with this question. What is the bidding curve in electricity market? Actually, the bidding curve is a pair including the quantity of electricity and electricity price, which both generator and consumer in the market are willing to trade the electricity at those specific pair. In our study, we investigated how to optimize the bidding curve for the charging station as one of the most important consumer in the market to maximize their profit. Generally, the bidding curve collect into different key markets, one day-ahead market and intraday market. Probably you know better than me what are this market. But in brief, day-ahead market is a forward market and generally open and close one day before in advance. And intraday market is another market come after day-ahead market and is much more closer to its delivery time. As a response to real-time change in day-ahead market. For example, change the weather may affect the generation of renewable energy. So day-ahead market must cover this fluctuation and imbalance in real-time in day-ahead market. But one most important point in this two market is frequency of the market update. I mean market time unit. In general, the day-ahead market updates every hour. 24 times per day, but in intraday market we have a different time unit, every 60 times, 30 times, and even 15 minutes for updating the market. Many of countries, especially European countries, are going toward 15 minutes time unit for updating the price in intraday market. As you can see, in single intraday coupling market. In July 2024, some of countries, the green one, including the Czech Republic, adopted 15 minutes time frame for trading intraday market, and is planned to March 2025. Some other countries add to this market. I'm not sure how much this plan is on track or not, but it shows generally the trend going toward a smaller and smaller time frame for trading the electricity. That's the reason we also consider 15 minutes time frame unit for our intraday market. It means that we need to optimize 96 bidding curve during the intraday market plus 24 bidding curve for day-ahead market. That is indicate complexity of our model, and it should be considered. The bidding curve is not only decision variable in our model, and we have some other decision variable, including operational decision variable for charging a station, how much we should buy the electricity from the grid, how much should be charged or discharged in battery or hydrogen tanks, and so on. And also we need to consider if the electricity price is subject to uncertainty, its complexity will intensify much more. Just suppose we have 3 stochastic scenarios for each quarter. Going forward and through 96 quarter, I cannot imagine how big will be our scenario 3. Even using some scenario reduction techniques, we are facing a problem with 1,000 or even million of scenario. And solving such a complex problem is not possible by traditional computational optimization algorithm or even commercial software. And we developed a decomposition approach, next slide, for solving this problem. We decompose our problem to the master problem and sub-problem first. The master problem is responsible for solving day-ahead market, and sub-problem is responsible for solving intraday market. And then we exchange the information, between the master problem and sub-problem, including we develop one strong optimality code. And also there are a lot of technical details that I invite you to check the original paper if you are interested to. But still, using this decomposition or sub-problem is not computationally feasible to solve. So, the source of complexity is 2 things. One, number of quarter, 96 quarter in the sub-problem is a very big number. And second, number of stochastic scenario price. Okay, so we follow 2 different approaches. First, we develop the second layer of decomposition. In this second layer, we decompose all sub-problem, but this time horizontally decomposition, and using the forward pass and backward pass for solving our sub-problem. And in the forward pass, we start from the first sub-problem to the last sub-problem, and the backward pass, we start from the last sub-problem to the first sub-problem. And in forward pass, after solving each sub-problem, we transfer the transition variable, including the battery level and hydrogen tank level, to the next sub-problem. And in the backward pass, we transfer the optimality code generated to the previous sub-problem, and we repeat entire process until our sub-problem is solved. But even this decomposition, horizontal decomposition, solving the sub-problem for thousands of stochastic scenarios is still impossible. So we adopt a kind of sampling optimization. I mean, instead of solving the sub-problem once for all scenarios, thousands of scenarios, we solve multiple, next slide, we solve multiple sub-problems for a small set of scenarios. For example, each set including 10 or 20 scenarios. And for that reason, we have to develop some special lower bound and upper bound for solving the stochastical upper bound and lower bound for solving the problem. And we develop one specific termination condition for our sub-problem. For example, if our stochastical upper bound fall within this domain or sub-problem terminate and stop, and then we exchange information with master problem and solve the problem, ensuring to reach convergence for entire model. And in the last slide, I would like to present numerical result provided by our algorithm for solving the problem in a specific setup. And in comparison with some other commercial software, even classical Bender's decomposition algorithm, as you can see in the table, the C-Place, Groovy, and classical vendors were not able to solve the problem, and generally they faced with out-of-memory error for solving the problem. But our proposed algorithm were able to solve the problem in 4-hour time unit after 132 iterations with much very close optimality gap, about 2.5% optimality gap. And in our convergence chart, you can see a stability of our algorithm with very smooth trend of convergence between upper bound and lower bound. and also effectiveness of our algorithm for solve and provide high quality solution in reasonable time. That was all my presentation, and thank you.
So hi, my name is Zdeněk, and today I will be talking about non-deterministic action reversibility. This work has been done in collaboration with University of Klagenfurt. Next slide, please. So action reversibility studies whether the effects of actions can be undone by other actions in the domain. It has been empirically proven that action reversibility is present in many deterministic domains that are researched in the literature, and it has application in robotics, system verification, for the guidance of search algorithms, and in other domains where reversibility naturally occurs. Next slide. Thank you. So before we will speak about action reversibility, we will need to learn about fully observable non-deterministic planning, in short FOND. So I will briefly summarize that. So we are given some variables that has finite domains that can contain some values that describe the states. Then we have actions that allows us to change the states of the environment from some state to another, and we are usually given an initial state and a goal state. And the goal is to find a policy that takes us from the initial state to the goal state. So we want to solve the problem that's described by the system. Next slide, please. On this slide, you can see an example of omelette domain. In this domain, we want to make an omelette for us. So we start in a state 1, where we have a pan with no egg on it, and we want to get to state 7, that's on the right bottom part of the scheme, and we can reach that state by applying 2 actions break in sequence, right? But this gets us to the state only if we are lucky, only if we go from 1 to 3 and from 3 to 7. This is caused by the fact that the actions are non-deterministic, so action break can fail. We can try to open the egg, but it can fail, and the egg can fall into pan with a shell, so we don't want that. That's denoted by state 2, and in this case we want to discard that again and move back to clear pan, clear it and start again. Or we can try to crack the egg, but it doesn't open, it's just cracked, and we need to open manually once again, and that's denoted by state 4. So we have these 3 actions that that takes us from one state to another. And yeah, we want to change the environment from some point to another. Next slide, please. So the contribution of our work was that we've defined weak and strong reversibility that's inspired by 2 notions that are presented in fond planning. One is weak policy. That's policy that has a chance taking us where we want to. It is not guaranteed whether we will get there or not. And the second one is strong policy. This is a policy that is guaranteed to succeed no matter what happens. Next slide. Therefore, we called action weakly as reversible if and only if from each state into which that action can result from some state S, we can return back. Next slide. Or strong if there is a guarantee that we will be able to return back. Next slide. We further focused on 2 specific classes of action reversibility. One is universally reversible. That is, if that action is reversible everywhere, we call it universal. Next slide. And the second is uniform reversibility. That is, okay, so this action is reversible in that states S, but it can each state can have its own policy, and we don't want that, right? We want to have one common policy that works everywhere, and that's all states. In all that states of the set S. So this is called uniformity, if there is only one common policy for it. On this example, you can see weak reverse policy for states 4 and 5 for action open. As you can see in these red states, you can apply that action. If you apply it in 5, you end in state 6, and if you apply it in state 4, you end in states, either in state 3 or in state 2. And as you can see from all these 3 states, 2, 3, and 6, if you follow the proper green lines, you are able to come back to the state from which you left by applying that action. So you say this action is weakly reversible because you have a chance to return it back. Next slide. On this slide, you see strong policy that works only for state 5. If you apply action discard that we want to reverse now in state 5, you end in state 1. And as you can see, if you follow green lights and you consider all possible changes, all possible effects, you will eventually get to the state 5, and you can't end up anywhere else. So this action is this action is strongly reversible in state 5. Next slide. So our work focused on universal and uniform reversibility. We have several theoretical results. One is necessary condition for strong universal reversibility. Then we have proposed, like the major result of the work is that we have proposed reformulations for weak and strong reversibility to classical and font planning. That means that we don't need it to provide algorithms for specific algorithms for solving action reversibility, and we could reuse existing planners that work with classical or font planning. Next slide, please. Next slide. Yeah. And we also have some experimental results. So we have investigated the reversibility of actions among the domains that are used in a community in the literature, and we have find out that we are able to prove some form of reversibility for approximately 68% of actions, where 1/3 of them was identified as universally irreversible, meaning that you can't undo the changes, and 1/3 as weakly universally uniformly reversible, meaning you have a chance to reverse it anywhere by the same policy. And the most important result is that 91% of these actions was proven as strongly uniformly universally reversible. That means 1/3 of actions can be reverted anywhere by the same policy, no matter what non-deterministic effects occur. So you can imagine a robot, and if you have strongly universally uniformly reversible action, you know that you can do that, and you are safe because you will be always able to come back no matter what happens. Next slide. So in conclusion, we have defined weak and strong reversibility for non-deterministic actions in font planning. We have specifically focused on strong and weak universal uniform reversibility, for which we derive several theoretical theorems. We have proposed reformulations to already existing widely studied formalisms, and we were able to identify that in total 56% of actions were reversible or irreversible. Thank you for your attention.
Okay, thank you, Jacob. Any question? So let me ask, so how large are these states that we are exploring?
Like that example that we had on the slides, it was like toy example. Usually these state spaces, they are easily bigger than the number of atoms in the universe. So the font domain provides you a compact representation of the state space. So the problem here is you want to essentially find a cycles in that graph, but you need to do it on that abstracted level. You don't have the explicit graph because it would be too big.
Did you try to apply it on some, I would say, real world, but not toy problems?
Yeah, we have a paper from 2021, I think, that's related to reversibility, where, for example, we used it to prove that nature that's present in that environment that plays against agent can eventually be undone, so that if, for example, if I want to go shopping and it rains, I can wait before it stops because it's reversible, right? Because the roads will dry out, and so you can examine reversibility even in this like real world scenarios. But yeah, it lacks applicability for this part.
Thank you. For the next talk, will be given by Peter. Please go ahead.
Hi everyone. My name is Petr Stejskal. Today I will talk about the control algorithm for new hybrid power plant. We work on this topic together with Ondřej Mamula, Přemysl Šůcha, David Hrycej, and Jitka Stoklasova. Please, next slide. I would like to talk firstly about background of the project. Maybe you heard about the power plant in the media. We work on this project for a few years. And also I'd like to highlight that this project is cooperated with Department of Professor Mařík, concretely Group of Energy, presented by Ondřej Mamula. And we are happy that last year we delivered a control system in the power plant, which is in operation since July 2024. Also, during this project, we cooperated with some important partners, namely Siemens, where we work together with on integration into their SICAM environment. Also, we cooperated with Centrax, which is a manufacturer of gas turbines, which are used in this solution. And we work together about detailed modeling of their gas turbines. And also, I would like to name DECI, which is a Czech company and is a final operator of this power plant. And more about this project and power plant itself, it will be presented later by Ondřej Mamula in presentation scheduled later. Next slide. Firstly, before the talk about control algorithm, I would like to say a few words about ancillary services. It needs to be in balance production and consumption in the grid, and this is task for transmission operator in Czech Republic. It's company CHEPS, and this company has opportunity to use some capacity reserve in the grid, which called ancillary services. There are many types, and we would like to focus only for one type, which is a further service. On the left side, you can see the figure about how this service could be activated. The red one are positive, so this means that there is added more generation into the grid, and gray one is that there is less generation activation. On the right side, there is example of how this activation can be looks like. That the red line is that there is some demand, which is control signal from the grid operator, and the provider, the power plant, is react on this signal like blue line. So please next slide. And I would like to talk about the problem statement. For the meet requirements of further services, we have available 6 gas turbines, and also there is a battery system which is able to of quick reaction, but it has limited capacity. In contrary, the arithmetic gas turbines has opportunity to run for a long time, but there are more complicated devices. So there is 16 states. There is relatively short startup sequence, about 2 minutes, but there is too long deactivation sequence, about 10 minutes. But with cooperation with Centrax, we are able to found some improvements about reactivation sequences. So in some states, we are able to start more quickly. About the problem of control, we are facing to uncertainty of after service, because this service can be activated for a limited time. So we don't know how long activation will be, and also there is no guarantee how amount of energy will be activated, so it can change every second in whole range which is cell. And so task for the control is to react to these demands, and what needs to do control must solve is something like a real-time unit commitment. And also, as a secondary task, there is optimization objective. So we are trying to minimize operation cost of gas consumption and electricity. And in our solution, we applied techniques of robot optimization. And also, would like to highlight that in this domain is very, very hard to decide when the turbine should be start, stop, or restart. About control algorithm design, I would like to mention 4 main components. We have here a scheduler, which is component which trying to planning in which time one of the turbine should be available in a state we called power state, where the turbine is capable to provide power, and also scheduling times when this turbine should exit this state. Then we have next component, which we call the manager. This component solving the cheapest combination to achieve this scheduled times. It can be defined as a min cost flow problem. And also there is economic dispatcher, which managing the output of power of turbines in power state. And as last component, there is a battery balancer, which compensating rest of the needed power, which are not delivered by turbines. Also, I would like to highlight in this solution digital twin technology. In this project, to solve this this control, we developed twins of turbines. It's based on a complex state model and fully parameterized. And also we modeled battery system, which were more easier, but also parameterized. And these digital twins help us to create a simulation environment of this power plant. And we were able to test our control against different various of scenarios. And we could see the outputs of the result of that scenario. To imagine that on the top right corner there is some graph as output how the power plant will be work. Thanks to this good basement, we could go into very clever architecture. We could design our control algorithm that the control algorithm can work with power plant interface, that it receives data from power plant and sending commands to it. But we added the same interface, and we were able to set our digital twins behind the same interface without changes in control algorithm. So control algorithm has is not able to detect if he controlling against real facility or our digital twin on PC environment. To conclude this is a unique power plant, so thus the unique control is needed to design. In our developer, we focused on effectivity of the solution with respect of robustness coming from a further service. And also we are happy that we not detected any crash shift of our solution and it's fully reliable. And also we are happy that we achieved very successful solution come into the industrial environment.
Okay, thank you very much. Any question? How long is the response time for the battery system?
The response time of the battery system is very quick, at most 2 seconds at full range of power, at maximum by our test.
So does the grid still need something faster than the battery system? Like there's something faster than 2 seconds?
I think that 1 or 2 seconds is okay.
Could you somehow quantify the contribution of your, let's say, control approach? How many money?
Yeah, it can be.
I will do later. Okay.
Okay, so I should respond? No.
Okay, that's fine. Okay, so that's the plan, right?
And this is real facility.
Okay, so there is subsequent talk by Ondřej Mamola. He will speak more about the facilities. Okay, thank you very much.